Thank you for the introduction, Tara. So in the previous talk, we've seen that in some applications of machine learning, it is important to protect privacy. And in this talk, I will present our approach at doing so. This is joint work with Martina Buddy, Ulvar Erlingsson, Ian Goodfellow, and Kunal Talwar from Google Brain. So in some applications of machine learning, the training data may contain some private information. And this is the case, for instance, when trying to learn generic facial recognizers. However, in 2015, a group of researchers found that by observing the predictions of the machine learning model, they were able to approximately reconstruct some of its training data. And later in 2016, another group of researchers showed that it is possible to infer whether a specific training point is included in a model's training data by also observing the model predictions, and they call these attacks membership inference attacks. So in these two cases, the adversary only has access to the model through queries. So the model is a black box for the adversary, and the adversary can select inputs and observe the model's predictions. However, when we're designing defenses, we'd like to protect against the strongest types of adversaries. And there's a lot of evidence that machine learning may be able to memorize some of its training data. And one piece of such evidence is another paper published at this conference titled Understanding Deep Learning Requires Rethinking Generalization. So we'd also like to protect privacy in the face of adversaries capable of inspecting the model parameters and the model's internal details. So our threat model in our work assumes two things, is that the adversary is both capable of making a very large number of queries to the system as a black box, for instance, but also that the adversary has access to the model's internal parameters. And before we begin, it's important that we agree on what we call privacy. And in our work, we used a gold standard of privacy, which is the differential privacy framework. So I will come back to it more formally later, but intuitively you can think of it as requiring that the same randomized algorithm on two input databases which are neighboring, which means they only have one training record that differs, the same algorithm should make outputs that are statistically indistinguishable. So under these assumptions, we'd like to design a generic approach at learning with privacy. And what I mean by generic is that it should not depend on the learning algorithm or the learning architecture. And this is a key distinction from most of the previous work that has been done in this area. And in our work, we provide both formal differential privacy guarantees, but also a certain intuitive notion of privacy that I will explain in a few slides. So our approach is the private aggregation of teacher ensembles, also known as PATE. So it should be pronounced like the French food. And it begins by splitting the data into n partitions. And on each of these partitions, you train independently a machine learning model. So there is no restriction on how you train these machine learning models. So they can be, for instance, complex models like deep neural networks. Once we finish the training to deploy the model, we'd like to make a global single prediction from all of the teacher's predictions. So we're going to perform an aggregation. So the first attempt would count the votes assigned to each class in the problem. So this is a classification problem. So we record all of the teacher predictions, and we would take the one that was assigned the most number of votes. So you can see how this would provide intuitively some form of privacy, because if most of the teachers agree on the same prediction, then it means that this prediction does not depend on a single training partition. So intuitively, this should mean that we should pay a very small privacy cost for this prediction. However, there is an unlikely, or there is a possible case where two classes would have a very similar number of votes. And if you output the prediction of the aggregated teacher in this case, you may reveal some private information. So this is why we add an additional step where we inject Laplacian noise to the vote counts before selecting the label that was assigned the most number of votes. And the introduction of this noise is what provides privacy because it obfuscates the cases where the teachers disagree and don't have a strong quorum. So we have this system here, the aggregated teacher, that can behave like, you can think of it as a differentially private API. You can submit inputs and it will return privacy-preserving labels. But it would be nice if we were able to train a machine learning model that we can deploy to user devices and they can just run the model to get predictions. And that is what we do by training an additional model called the student model. So the student model has access during training to a pool of public data that is unlabeled. So in order to train the student, we're going to ask the aggregated teachers to label the public data in a privacy-preserving fashion. And so in a sense, we're transferring the knowledge from the teachers to the student in a privacy-preserving fashion. So there are also multiple reasons why the student is beneficial from a privacy perspective. If you look closely, the aggregated teacher violates two of our threat model assumptions. First, every time you make a query to the aggregated teacher, you increase the privacy cost because each response given by the aggregated teacher may potentially reveal a little more private information. Whereas once the student is done training, it has made a fixed number of label queries to the teachers, so the privacy cost is fixed. And we can deploy the student. It can respond to as many queries as we want from the users. It will not change the privacy cost. The second reason is that, if you remember, we assumed that we should defend against adversaries that are capable of inspecting the model parameters. And if the adversary has access to the teacher parameters, since the teachers were trained on private data, it may recover some of the private data through the teacher parameters. Whereas the student is trained on public data with privacy-preserving labels. So in the worst case, for us, if the adversary is able to recover the training data of the student by examining its parameters, it will only be able to have access to the labels that we protected with privacy, so the student will not leak more private information than we intended. So we have this system once the student is trained. The nice thing is we can just get rid of the teachers and the training data, which is private, and simply keep the student as the model that we deploy to our users. So to formally prove the guarantees of our approach, we use differential privacy, as I mentioned earlier. And a randomized algorithm is said to be differentially private if for two databases which are neighboring D and D prime, and all possible subsets of outputs S, the probability of the algorithm outputting S on D is within a small interval of the probability of the algorithm, the same algorithm outputting S as well on D prime. So the size of this interval is characterized by the parameter epsilon. And so the smaller the value of epsilon is, the stronger the privacy guarantee will be. And in addition, we have a parameter called delta, which is a failure rate at which we tolerate that the bound does not hold. And it simplifies the privacy analysis while still providing strong guarantees. So we applied the moments accounted technique, which was introduced last year. And the nice thing is that it reflects some of the intuition behind training multiple teachers, in the sense that with the moments accounted technique, when we have a very strong quorum among the teachers, we end up paying a very small privacy cost. So we end up having very small values of epsilon. And finally, when we are training the student, so in the empirical setting, what we do is we record the votes assigned by the teachers, and this allows us to compute empirical values of epsilon, which we use later to evaluate our approach. So before I move on to the experimental results, I'd like to present a generative variant of PATE, which is PATE-G, which you can think of a more fancy version of PATE, that we designed for one simple reason, is that we wanted to reduce the number of labels that the student needs to train itself. And the reason that we wanted to do that, again, is that the smaller that number is, the smaller our privacy cost will be as well. So we use generative adversarial networks, which is a framework where you have two competing models. So the generator takes random noise and tries to produce samples that are similar to the real distribution, and the discriminator is trained to distinguish real inputs from the distribution from the ones generated. So in our case, we use a small variant of that framework where the discriminator is also asked to classify the real inputs in their correct classes. So this allows us to train the discriminator in a semi-supervised fashion where we only have part of the data that is labeled. So in PATE-G, we replace the student model from PATE with the generator and discriminator. And so the discriminator is going to be our classifier. So at test time, we simply deploy the discriminator, which acts as the classifier, and we can discard all of the other models. So I'll conclude with our experimental results. We performed experiments on 4 datasets, so 2 image datasets, MNIST and SVHN, and 2 UCI datasets, the adult and diabetes dataset. For the teacher models, for the 2 image datasets, we use convolutional architectures, and for the 2 UCI datasets, we used a random forest for each teacher. And then we trained the student using the GAN approach, so the PATE-G framework for MNIST and SVHN, and the normal PATE framework for the UCI datasets. By the way, all of our experimental setup is on the TensorFlow models repository if you'd like to check it out. So in this figure is basically plotting the aggregated teacher's accuracy, so before the student is trained, with respect to the privacy that it provides for each individual label. So on the x-axis is the epsilon value for each query responded by the aggregated teacher, and on the y-axis is the average accuracy of that prediction. So with 10 teachers in the ensemble, you can see that as we reduce the value of epsilon, which means we introduce more random noise to provide stronger privacy guarantees, the accuracy of the aggregated teacher predictions goes down very quickly. Whereas if here on the up part of the graph, if we have 100 or even 250 teachers in the ensemble, then we're able to maintain better accuracy for much smaller values of epsilon, so for much stronger privacy. And so we use these labels to train the student model. So here again on this graph, now we have the epsilon value for the student, which means for the this is the overall cost of our approach. And on the y-axis is the error rate of the student, which is privacy preserving. So lower values are better on both axes, and ideally we'd like to be in the origin. So in purple and blue, you see for MNIST and SVHN that we greatly reduce the value of epsilon, which means we increase a lot the privacy guarantee while having a negligible impact on accuracy or even improving accuracy because the error rate is lower. And for the adult data set, we bring the error rate close to the state of the art for a non-private model while paying a modest cost in the privacy guarantee. And finally, for the diabetes data set, we observe something very interesting is that the accuracy of the privacy preserving model is higher than the accuracy of the non-private model. So to conclude, I'd like to stress three things. The first is that the approach is generic, which means two things. You can apply to many different types of classifiers, including neural networks, but also, even if you have little background in privacy, you can contribute to privacy-preserving machine learning by improving the individual teacher and student models within the PATE framework. Second, our privacy bounds are meaningful, which is not a given, and they achieve state-of-the-art trade-offs between accuracy and privacy on MNIST and SVHN. And finally, as I mentioned in the previous slide, we observed that privacy and generalization are not necessarily conflicting. So with this, I'd like to thank you for your attention and take any questions you may have. I invite you to visit our poster this afternoon. And also, if you'd like some swag, we don't have real pate, but we have t-shirts, and there are a few left. Thank you.
Hi, I have a question. So if you have like n equal 250, then you essentially have to split the data 250 ways. Like so for higher number of teachers, you have to split the data into smaller amounts. Does that present a problem for learning?
Yeah, so there's sort of a sweet spot. As you increase the number of teachers, you generally are able to increase more, to inject more noise, which means you can provide stronger privacy. But at some point, you have so little data to train each individual teacher that their accuracy starts to go down, the individual teachers, and so you're not able to provide accurate predictions with the aggregated teachers. So the number 250 happened to be the sweet spot for MNIST and SVHN. For the UCI datasets, I don't have the exact number, but from what I recall, it was 100. So it's dependent on the data set. In the paper, we have a small discussion of what's the influence of the number of teachers on the privacy.
Okay, so this is an analytic bound?
Yes.
Okay. So you have a bound and you optimize the bound and you get 250 around.
So the value, the optimal value of the number of teachers, we found it by doing a grid search, basically.
I see.
Yeah.
Okay. Okay, another question. So like, it seems like your method doesn't prevent an attack on the teacher, like a white box attack on the teacher, right? So you still suffer the same problem as before.
Well, first of all, we haven't tried attacking the teacher. So the way that you could, the most likely way you could attack the teachers is by looking at their individual parameters.
Right.
I'm not aware of like a demonstration of exactly how to do this, but in our threat model, we operate in our threat model with the student. So the student is the one model that is able to protect privacy both in the black box and white box threat model while being accurate.
I see.
Yeah.
Okay. One last technical detail. Is there advantage to using like exponential mechanism instead of noisy argmax for the aggregation? Sorry,
I didn't hear that.
So instead of doing a noisy argmax, can you do an exponential?
Yeah, we actually experimented with this. The noisy argmax was the one that worked the best.
Okay.
But I'm sure there's a lot of work to be done in this. There's also one thing here is that our analysis is quite pessimistic because in order to be completely generic, we assume that if you change one point in the training data in one of the partitions, it may change completely the predictions of the corresponding teacher.
Right.
And so you may be also able to provide stricter bounds by making some assumptions on the way you're training the teachers, but we didn't want to do that.
I see. So essentially you just had the vanilla DP grant
yes.
setting, right?
Yeah.
Okay. Yeah.
Hi. Thank you for your talk. What would be the disadvantage of partitioning the different teachers, but with overlapping partitions of data? Would there be a strong disadvantage to that, to try to minimize the risk of having too small data in each teacher?
It just makes the analysis more complicated because, again, if we want to be able to have a completely generic approach, we cannot make any assumptions of the influence of specific points in a partition on the output of the corresponding teacher. So if you have overlapping partitions, it becomes harder to know what will be the impact of changing one point on the teacher votes.
Okay, let's thank the speaker.
Thank you.